Hello everyone, my name is Subhrata Samanta and I am from IIT Kanpur. So, I am your tutor for the physics subject. So, in the previous class, we will calculate the electric field due to a ring at the origin as well as the distance from the origin in the perpendicular distance, okay, at a point P, okay, and the distance is z from the origin, and we got this. So, today I will calculate at what distance the electric field becomes maximum. Okay. So, to do so, first we do a derivative d E z or del z with respect to z. So, derivative this got that 1 over 4 pi epsilon naught q, right, and so first derivative z and then r square plus z square 3 by 2 minus, so basically plus q z, and this is q z times minus 1 over r square plus z square 5 by 2 times the derivative of this, so 3 by 2 times r square plus z square, no, this one is already considered, minus 3 by 2 and times 2z. Okay. So, then the becomes, if we take about 1 over 4 pi epsilon naught r square plus z square 3 by 2 1 minus 3 z square divided by r square plus z square, okay, and this one becomes, so q over 4 pi epsilon naught r square plus z square 3 by 2 r square minus 2z square z square. So, at maximum value, okay, of Ez, so del Ez over del z becomes 0, right. So, at maximum point del Ez over del z becomes 0. So, this implies that r square minus 2z square becomes 0. So, z r over root 2, right. So, at a distance z, okay, so this is basically 1 over root 2, right, this one is minus 1 over root 2. So, at a distance z from the center in the perpendicular axis, okay, and at distance r by root 2, the electric field become maximum, okay. And the maximum value, if we calculate the maximum value of the electric field, so E, the maximum value, so E at point z equals to r by root 2, just plugging into this the expressions in these expressions, in this expression. So, 1 over 4 pi epsilon naught q and z is r over root 2 by r square by 2 plus r square, the whole to the power 3 by 2. So, this one becomes 1 over 4 pi epsilon naught q r, okay, by root 2 divided by, so this is 3 r square, okay, and divided by, so 3 r square, the whole to the power 3, and this one is 2 root 2. 3 by 2. Okay. So, it is basically 1 over 4 pi epsilon naught. So, this root 2 to cancel. So, 2 q r over 3 root 3 over r cube. Okay. So, this is the maximum value, okay, and we divided by E naught. So, E max divided by E naught. So, where E naught is 1 over 4 pi epsilon naught q over r square, right. So, this is basically r square. So, 2 by 3 root 3. Okay. So, just check this one. Yeah. So, this is the maximum value in the graph. Okay. So, this value. So, this value is 2 by 3 root 3. So, next we will going to discuss the other type of charge distributions, okay. So, like the surface charge density, right. So, surface charge density. So far we discussed that how to calculate the electric field due to a line charge density, right. So, that means the charge distributed over a line. Okay. So, now we are calculating the electric field due to a surface charge distributions, that means the charge distributed over a surface, okay. And then I will going to the discussions where the charge distributed over a volume. Okay. So, going step by step. So, in the surface charge density, so we consider a surface S, okay, of area A. So, we consider a surface S, okay. So, the area of the surface A, okay, similarly to the length, okay. Suppose you consider a rod and the length of a rod is L, okay. So, in this case we consider a surface S and the area is A and the charge is distributed. So, charge is distributed over a surface S, okay, of area A. Okay. So, with a surface charge density, surface charge density sigma, right. So, it denotes the surface charge density is sigma, right. So, in principle the sigma as a function of r, okay, that means that depends on the distance sigma. So, in general functions of r vector is dq over dA, right, and the dimensions of sigma. So, again dq is the, we consider a small strip, okay. The area of this strip is dA, okay, basically small element, okay. So, in this case it is a 2D element and the area of this element is dk and the charge is dq. So, the charge is dq and the area is dA, okay. And the sigma as a functions of r, because where we consider this strip, okay. So, let us say from center. So, if we draw a axis, so from center to this element the distance is r, and the dimensions of sigma is, so dimensions of charge by the dimensions of area, so coulomb per meter square, right. So, this is the unit, okay. And the total charge, how to calculate the total charge? So, the total charge on the entire surface is q. So, now we do the surface integral instead of line integral, right. So, double integral means the surface integral, yes. So, there is a two variable in the Cartesian coordinate dx and dy. So, that is why the two integral represented the surface integral, and sigma as a functions of r vector times dA. This is a small element, area of a small element. So, next we calculate the charge for a certain system and then the electric field. Okay, yeah. So, one more thing, if the charge is distributed uniformly over the entire surface, then sigma is not depends on the distance r. Okay, so this is constant and we can taken out of the integral. So, we will solve a problems, okay, and it becomes more clear. So, let us start with an example. Yeah. So, electric field due to a uniform charged disc. So, example, electric field due to a uniform charged disc. So, here we consider disc instead of circle, okay, or ring, because you consider the surface charge density. So, uniform charged disc of radius r with a total charge q, so lies in the xy plane. So, we consider a z axis and so now onwards we are considering the 3D system, okay, and this one is x, y, and this is the z. So, we consider a disc, charged disc and uniform over the xy plane, okay, placed. So, this is charged disc, okay. So, a uniform charged disc of radius r and total charge capital Q. So, we calculate the electric field at a point P from the origin, okay, and the distance is z. So, how to calculate? So, again, so we construct a small element. So, in this case we choose a small element with a charge dq, right, because this one is a surface, right. So, we consider element on the surface and not considering a strip, okay. So, we will continue this in the next class, okay, and calculate the electric field due to this charged disc, okay, and then we are going to the volume charge density, okay. So, thank you.